Hello, Mr. Stone here, and today we are going to be looking at two-sample t-tests. And there are a number of ways to do two-sample t-tests. In particular, today we're going to be looking at what to do when sample sizes and variance are equal. And we're also going to be looking at a one-sided two-sample t-test here. Let's take a look, first of all, at our data. So suppose we've got two groups, and let's say that they are doing a math problem test. How many math problems can they do? Maybe you've got your math teachers over here, and then you've got some professors over in group B. Okay? But the important thing here is that we grab a sample. We're grabbing a sample here of 15 in each group, and we get the mean for that sample. In this case, in a set amount of time, we can say that 88 math problems are done by the math teachers, and 91 are done by the math professors. All right, we see that there is some difference in the sample means, but is this difference really significant? We see that there's going to be some standard deviation, right? There's going to be a little bit of overlap. Is it enough to say that the professors did better than the teachers? Well, let's examine that further. The first thing we're going to need to do is come up with our hypothesis. Did Group B perform significantly better than Group A? And our null hypothesis, let's just set that they are equal, that there's really no change. One is the same as the other, Our alternative hypothesis is to say that, you know what, I saw that the mean for B was a little bit greater than 88. I'm going to think that that's significantly greater than my population mean for the first group. So overall, Group B performs better than Group A. Maybe not by a whole lot, but at least significantly enough that we should expect that in the population means. So let's gather up all of our data here. So notice I've got a lot of the stuff we've seen before. We've got N1. I'm putting 1s for everything in Group A, 2s for everything in Group B. I've got 15 samples in each. And there are my standard means. I've also got my standard deviation for the samples, the S1 and the S2. Okay, we see that there is a little bit of deviation there, not a whole lot. Let's see how this plays out. So first thing we need to do is figure out what our standard error is going to be. This is a little bit different compared to what we've looked at already. Our standard error for the difference between these two sample means is going to be the square root of 1/2 times the quantity S1 squared, this is my standard deviation from the first group, plus the standard deviation from the second group squared, all of that, the square root of all that, times the square root of 2 over n, where that is my sample. So I'm going to start plugging in here. So this is equal to, I said that I had a standard deviation for my first group of 1.8. So that's going to be, okay. That's going to be 1.8. Excuse me. Don't want to put my parentheses just there just yet. 1.8 squared plus, for my second group, that was 2.1. So that's going to be 2.1 squared. Need a little bit more there. All that times the square root of 2 over n. And n, let's plug in for that, we said was 15. So if we do the calculations there, we'll see that we get 1.956 times 0.3651. And if we follow through with that, simplify that, we'll get equals 0.7141. This is the standard error of the difference between the two means. Now that we've got that, let's get our t-score for the difference between these two means. And that is just simply going to equal x bar 1 minus x bar 2 over that standard error that we just found. So let's start plugging in. 88 was our first mean for group A, minus 91 over 0.7141. We just found that. We're plugging in there. And that should give us negative 4.20. So this is our t. Now, we've got that, but we need to go back and think about, hey, this is a t distribution, so what is my critical t value? Where am I going to say, oh boy, if it's past this mark, then my probability is so low that I need to reject my null hypothesis? Well, we need to get our degrees of freedom first. And what are our degrees of freedom? When we're doing a two-sample t-test like this with the same variance, same number of samples in both, it will simply be 2n minus 2. So we plug in, we said that our n for both of these guys was 15. That'll give us 28. So on your z-score table, or excuse me, not z, t is in Thomas. On your t-score table, look up for where t of 0.95 would be with a degree of freedom of 28. And you should get 1.701. Now remember, if we sketch out our t distribution here, that here's our mean, it's 0. We are concerned about if mu1 is less than mu2. So we're going to be looking to the left. So we'll need to change this 1.701 to negative 1.701. That is where our critical t is going to be. And our t-score for our difference between these two samples was negative 4.20. That's like way over here. Okay, negative 4.20, that is the difference. And it is so far over to the left, it is beyond our critical value. It's over here, the probability is so low. Remember, it's 0.05 for everything going up to our critical value. Okay, so everything here in red is 0.05, but we're cutting it. We're only looking at this part right here. So that tells us that this section is going to be smaller than 0.05. This is our probability, therefore p is less than 0.05. We said our null hypothesis was that the two population means were equal to each other. Because p is less than 0.05, we reject that, and we are inclined to believe that our alternative hypothesis may be true, where the population mean for mu1 is less than mu2, in which case it would be that the professors are likely to score more than the teachers, the math teachers, in general. That's what our statistics lead us to believe. So review this. We'll talk about it more in class, and I hope you have a great day.